Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today, the work today, I will mainly talk about the network part of my research. So here's the outline of the talk today. First, I will talk briefly about bandwidth-asymmetric networks and why are we interested in these type of networks. And then I will talk about the problems of doing data dissemination over such bandwidth-asymmetric networks. I'll talk about the related work, and I will define the throughput efficiency. Okay, to basically using this throughput efficiency, we can figure out the bound of any algorithm and topologies, the optimal bound. That is to say, given this bound, I can guarantee you that none of the topologies or any algorithms can perform better than this bound. So, okay, and then from this bound, we propose a whole bunch of optimal topologies for special cases. But of course, having optimal topologies is useless unless you build something. So I will show you the result of our deployment of our system. We deploy it on the Planet Lab. Okay, and I will conclude my talk with some of the preview of my research in the multimedia networking lab at Oregon State University. Okay, so why are we interested in bandwidth-asymmetric networks? Well, if you think about it, if you look at digital describer loop, right, it is inherently asymmetric. You have much larger download bandwidth than upload bandwidth. So typically, upload bandwidth is 100 kilobit per second, right? Depending on how much you pay. You can get a little bit more if you pay more. But the download bandwidth, on the other hand, is typically about 1.5 megabit per second up to 10 megabit per second, if you are willing to pay for it. So there's an inherent asymmetric bandwidth, and this is based on the design, right? Because most of people like to download, not to upload. They like to surf the web. So this is the reason why download bandwidth is higher than the upload bandwidth in DSL. Okay. So this is one type of network. This is popular, and we like to do data disseminations in this type of network. Okay, now second type of network is wireless mobile networks. If you think about it, again, it is asymmetric, right? Why? Because if you think about it, the transmission rate usually is smaller than receiving rate, and there's a reason for it. Because to transmit a bit is a much more energy consumption than to receive a bit. So you want to minimize the transmission rate, right? So this is basically the energy constraint. And that's why, again, you have the scenario where you have the upload bandwidth is a lot smaller than the download bandwidth. Okay? Now, but in general, if you think about it, many networks, even the internet, they tend to put a limit on the sending rate than the receiving rate, right? If you think about it, for example, when you send a video, say a video is 2 megabit per second, yeah? The video generate a fixed bandwidth, then that's the upper bound bandwidth, right? So if you have a live video, you cannot send more than 2 megabit per second because that's a live video. So that, once again, you have a limit on the sending bandwidth, okay? But the receiving bandwidth, you can have, a T1 line, but you still receive only 2 megabit per second because, again, the source is constrained. Okay, so there's many scenarios where it's appropriate to think of the networks as asymmetric bandwidth networks. Okay. All right. So that's asymmetric bandwidth network. Now let's talk about the application of data disseminations. There are many, right? P2P applications become increasingly popular, right? We have streaming applications, we have video conferences, multiple persons video conferencing. We have video multicast, and we have large file distribution programs, right? On network like Nutella, BitTorrents, right? We also have content distribution network that data needs to replicate it at the edge servers. Okay? So there are plenty of applications that use data dissemination. Okay? So now, let me talk a bit about data dissemination using traditional multicast. Well, everybody knows that traditional multicast is not optimal. And here's the reason why. Right? So here I show you a pictures of traditional data dissemination schemes using either IP multicast or an overlay multicast. Okay? An IP multicast is where these guy right here are router, and these guy are router, and these are the end hosts. But in an overlay multicast, all of these nodes are the end hosts. Okay? So why is it inefficient? Okay? Well, let's look at this. If this is a source host, okay, typically in multicast, you would send the identical data to both of the branch. Okay? Now, suppose this branch right here has small bandwidth. Okay? Then, this guy right here will receive, D2 right here, will receive a small bandwidth. Okay? Now, as the result, these nodes down here would receive a small bandwidth as well, because this guy right here receives smaller bandwidth. So even though this link and this link right here has high bandwidth, right, it cannot be used to send this data because this data is inherently limited. Okay? So therefore, all this node will receive less bandwidth, less throughput. Okay? So this is inherently because of the way we constructed the graph. Right? Now, a more efficient topology is not to use the tree and do some smart data partitioning. Okay? So suppose if this source right here, instead of send identical data, okay, you send distinct data. So partition A, partition B, and then this node somehow connected to this node and send A over here and B send over here. Suppose these are large bandwidth link. So this node right here now will receive complete data, A and B. Okay? Similar here, this node will receive both A and B. Okay? But because you have additional data coming from this direction, so now this node will have enough data, and then it can broadcast both A and B down here. Right? So obviously, this is a more efficient topology. Right? It's not a tree. Okay? It's more like a mesh. And then you have to do some data partitioning here. So the question is how to do smart data partitioning and how to construct this graph, right, to be efficient. Right? We have not talked about what is an optimal graph. But if you notice that even when you do this, right, these nodes right here, and these and these, they are not optimal because they are not active. If these are overlay nodes, that means they should contribute the bandwidth to the system, but now they are at the leaf node. They're not connected to any other node. So they are basically, they have the upload capability, but they don't do anything because they are leaf node in this construction. So we know that this is suboptimal. This graph is suboptimal. Okay? So this whole example just give you an idea that data partition and topologies are very important for efficiency. Okay, now efficiency in terms of throughput. I'm talking about efficiency in terms of throughput, the average throughput that every node receives the data. Okay, so there are a lot of work in this area. Split stream, for example, in 2003, they proposed to do data dissemination where they use multiple multicast tree. And it has this property that most likely the internal node of one multicast tree is the leaf of the other. Okay, and if you design that way, then of course you can make all the leaf node transport the data. Okay, so this is an approach that split stream took. CubeNet, also from Microsoft, also purposed something similar, and where they also use multiple multicast tree, but they also incorporate in the multiple description coding for video, and they send different description on a different tree, so that the receiver video will get more, will have higher quality if more description is received. So each of the receiver would subscribe to multiple trees. Okay? Informed overlay network is an interesting work. It was first published in 2002. In here, instead of construct an overlay network, they sort of randomly send the partition randomly to all the nodes. And these nodes would do some data reconciliation technique to recover the original data. And Bullet is also a similar work like informed overlay networks. Okay, so these are a lot of works that start this entire field. But now I want to introduce a different type of data disseminations. Mainly the difference is that we are dealing with the source constraint network and bandwidth asymmetric network. If you look at other works, they're dealing with networks which where the constraints are associated with the edge, right? And it makes sense. In a lot of network, the constraint usually is how much bandwidth you have with this link. They never say how much bandwidth you associate with the source, right? But in this case, if you we consider the constraint is associated with the source, and here's the reason why. But first, let me introduce the traditional problems in the edge constraint network. So typically, you have a graph, and you have nodes here, and you have edge, and each edge you associate with a weight, and these are the constraints. Okay, so you have different algorithms that find a specific goal, that accomplish a specific goal in this graph. For example, if you do one-to-one transmission, then you have algorithm like max flow, in which you find what is the maximum flow from one node from the source node to other node, and you have one-to-many. That this is an embedded max flows. And then you also have network coding. So there's a lot of algorithms to run on this kind of graph. But if you look at this graph right here, you notice that I move the edge here to the source. Okay, now the constraint is in the source rather than edge. So what does it mean? Well, what it means is that this source right here, it can either send 4 units over here or 3 units over here, but the total has to be 7. Right? So it has more degree of freedom in some sense. And it makes sense. You look at the DSL network, right? Look at the DSL network. If you're sitting at your computer, okay, and you want to send, say, 50 kilobit per second to this hole and 50 kilobit per second to the other holes. Well, what really happened at the underlying, at the physical layer, is you still go through the same line. And the one line is still 100 kilobit per second. So you're constrained by the physical bandwidth. You're not really constrained by, you not really have the freedom to arbitrarily change the edge, right? Your constraint is still basically that 100 kilobit per second that you have to send out. So you can choose to send maybe 70 kilobit per second this connection and 30 kilobit per second in another connection, but the total has to be the same. So this is why I'm trying to model the source network, because the source constraint network, because it's modeled a lot of the existing network out there. Okay. Now we're not talking about network congestion yet. Okay. We're just talking about suppose you have a physical bandwidth limitation. Okay. Okay. So you can see that how the asymmetric bandwidth can be viewed as a source constraint network, right? Because look at this. I don't really. If I view this network as a bandwidth asymmetric network, that means that if I send 4 out and 3 out this way, I know this node will receive it. I don't care whether 6 have the receiving bandwidth of 1. So in this case, I assume that 6 have infinite bandwidth, so you can think of that way. Sorry, I assume that this node right here would have infinite download bandwidth, right? Because I know if I send 4 bit per second out, that node is going to receive 4 bit per second. Okay, so that's the assumption here. So that's what I meant by asymmetric bandwidth. So upload is limited, but download is not. Okay. Okay. So here's the problem formulation. So given that we agree on the definition of asymmetric bandwidth networks, okay, and we are now I'm going to throw out an abstract problem. Suppose I throw out a whole bunch of nodes, and I'm going to tell you that this is a source node, and it has capacity of C0. And I'm going to tell you this is one of the receiving node, and it has capacity of C1. Okay? Now the question is, how do I construct a path through all of this, or a graph through all this node, so that this guy will disseminate data as fast as possible through all the node? Okay? So first we have to construct the graph, and second, how do we do data partitioning? Right? So for example, if I'm going to send, if C0 going to send, say, a partition C to C3 and partition B to C10, partition A to C4. Okay? And then I'm going to send, and I also associate the rate with each of these partitions, like how fast each of these partitions go. And then the next time step, C3 will forward whatever it received to C5, and similarly, C4 will forward whatever it received to C1 and C2. Okay? And then the next time step, C3 here will forward to C2, C9 will forward to C2. So now you notice that C2 got all A, B, C. So in this case, C2 got the complete data, right? The entire data, right? So we know this graph. So we know this graph is good for C2, but how about C1? How about others? How about other nodes, right? We don't know. So the question is, well, how do we partition this? At what rate? I mean, first we have to construct the graph, and at what rate we should send, or even, how many partitions should we send out? So it's a really hard problem, right? Okay, it turned out that this can be formulated as a mixed integer programming problem. Okay, you can sit down and model it and write out a whole bunch of constraints and write out the objective. But the problem with this is the number of variables increase exponentially with the number of nodes. So it's impractical. So you can't solve it. Okay. So, but if you notice that I have this paragraph right here, and it said that we want to find the maximum efficiency, but we haven't defined what is maximum efficiency. What is it? So we'll define it next. So the idea here is how to define the graph and at what rate we should send these partitions out. Okay. So let's define the efficiency. So let's define throughput efficiency. Okay. So I define throughput efficiency as the summation of all the useful sending rates. I will explain term by term later on. As a summation of all the useful sending rate divided by the minimum of the summation of all the capacity of node, or the number of leaf node times the capacity of the source node. Okay? So 0 here denote the source node. Okay? And then we have I equal 1 to n is the destination node. Okay? Si is the sending rate of node I. This is a useful sending rate, and I define what is the useful sending rate later on. Ci is the capacity of the sending capacity of the node I. Okay, so if you agree with me this definition, and I claim that for any data dissemination and any topology, pick any topology that you think is optimal, and pick any data dissemination that you think is optimal, you can always show that E is always smaller than or equal to 1. In fact, the optimal topology is the one that produces E equal 1. Okay? But it's not always possible. It's not always possible. But if you find a topology that has E equal 1, you know for sure you can't do better than that. Okay? But it's not always possible that you can find E equal to 1. Okay? So let's take a look at this definition and why is it true. Well, and at first let me explain what is the sending rate first, useful sending rate first. The useful sending rate is something like this. Let me go back to this graph right here. Okay. Now, look at this C right here. Okay, this C2 right here, this node right here. So C9 send partition B here, C3 send partition C here, and C4 send partition A here. Okay. Now, if C1 also send partition A here with some sending rate, this would be not useful because C2 already got the data from C4. So therefore, the useful sending rate is only the summation of the sending rate of all the distinct data packet. That's I define as a useful sending rate, because you obviously C1 can also send the duplicate data through here, but it could be useless as far as C2 is concerned. Yeah? So that's what I meant by useful sending rate. Okay, now, so this sum right here is the total of the useful sending rate of all the destination node. Here, the denominator is the minimum of the summation of all the capacity of the of all the node, and then the number of destination node type the capacity of the source node. Okay, now we want to prove that E is always smaller than or equal to 1. Well, it's very obvious, and that's why I just show you the proof. It's very obvious why it is true. Well, suppose there's two cases, right? There's this case and this case. This case saying that suppose the minimum of this quality here is equal to the first quality. Yeah? Then obviously, if you look at this definition, then you have the efficiency would be equal to this divided by this. And obviously, it has to be equal. It has to be smaller than or equal to 1 because this is your sending capacity and this is the actual sending rate, right, that you have to send. So therefore, this sum has to be smaller than this. So that's smaller than 1. Obvious, right? So why would a node? So we would ask, why would a node does not send as its full capacity? Well, it could be the constraint, because it could be that some other node already have the data that it needs to send, so it doesn't need to send that data to that particular node. So therefore, that's the problem. If you don't create a topology correctly, all right. So this case is obvious that we have the efficiency smaller than 1, and for this case, it's also obvious, but you have to think about it a little bit. So suppose that the mean of these two terms is this, yeah? And so E now, the efficiency now equals this. Now, if you think about it, the total maximum receiving rate is N, is the number of the node times C0. This is the number of the destination node times the capacity of the source node. Think about it. It's true, right? Because the source node can only send out the maximum of C0. So the maximum receiving rate of all the nodes at most is only N times C0. You can't do better than that. Right? Doesn't matter what the topology you have. So this statement is true. The maximum total receiving rate is this. Now, how about the total useful sending rate? This. Right? Well, look at this. The sending rate doesn't matter in what system, what topology you have. The sending rate, the total sending rate must equal the total receiving rate. Bit conserved. Right? The number of bits you send out must be equal to the number of bits you receive. So bit conserved. So this statement saying that, well, it doesn't matter what topology you have, the sending rate, the total sending rate has to be equal to the total receiving rate. Right? Okay? But the total receiving rate has to be smaller or equal to the total maximum receiving rate. Okay? And so therefore, this right here has to be smaller than this. This is receiving rate. This is maximum total receiving rate. So this has to be smaller than this. So it has to be smaller than or equal to 1. Okay? So now let me give you an example of throughput efficiency for a simple graph. Right? So you take this, say a graph that has a straight line like this. And if I send out data A here, a partition A here, and this guy could relay its data all the way through the N node. And suppose that all the nodes have equal capacity. Well, I claim that in this case 1, and it's optimal. You can't do any better than that. Well, why E equal 1? Well, you calculate all the sending, this is I equal 1 to N. So this is all the actual sending rate. So you have 1, 2, 3, 4. Yeah, and here you have N equal 4. Okay. Well, I just assume C0 and C1 equal 1. Okay. So then the minimum is this term. So E is still equal 1. So in this case, it's maximum. So for the node that have equal capacity, right? This is optimal topology. Well, but then you have many optimal topology. If you look at the same scenario, now you have this topology. In this case, I have a complete graph. So this guy would send C here, B here, and A here. And this guy in turn broadcasts its data to the rest of the two nodes. And this guy broadcasts its data to the rest of two nodes. This is also optimal. Yeah. So here, exactly. Yes. Ah, I should read up on that. Oh, okay. Okay, so this work was done last year also. But I think this is interesting. I should read up on your work then. Yeah. Yeah, yeah. So obviously, for this is achievable here. By just any configuration doesn't have to be equal. Doesn't have to be equal. Mm-hmm. Mm-hmm. Yeah, so that's a much more general case. Yeah. Uh-huh. Right. Yes. Yes, yes. So you are definitely right, but I definitely should read up on that work. Yeah. Okay, so it's very clear why E equal 1. All right, so you just mentioned it. Chain topology, long delay. Fully connected topology, large L degree, and it's bad. Large L degree is bad because when we're talking about peer-to-peer network, if one node leaves, if you have a lot of degree, have a lot of edges connect to that node, that means a lot of other nodes are to be affected, right? So that's bad. So we don't want, in practice, we don't want to have this kind of node if we want to scale this kind of topologies. If we want to scale up to, say, 1,000 nodes or even 100 nodes, this is not good, right? So now, so we have to consider the practicalities of these topologies. So now, let's see if we can do better, right? So we want to build a topologies that first, all destination node has to receive complete data because it's a must, right? We want small end-to-end delay for streaming applications, and we want small nodes out degree to reduce number of affected node when a node leaves the network. Okay, and then we want some sort of bandwidth fairness to promote resource sharing, also, and we want optimal bandwidth usage. Okay, so that's what we want. Okay, now let's see if we can do this. Okay, now the thing is, I noticed is that the thing is that in these streaming applications, usually the source have a fixed bandwidth. It sends out a fixed bandwidth, right? So in some sense, you can think of, well, every node should also send out the same bandwidth that it received to be fair. Okay, and also you think about it, it is constrained anyway. That bandwidth is constrained. It's the source, it's a live node. It's a live video. It can't go faster than that. So in some sense, you think about it, we want a topologies. We want now our problem reduced to, well, to a problem where all the nodes have equal capacity in some sense, right? Well, we will extend the case where all the nodes will have nodes that have different capacity, but for now we consider the case where all nodes have the same capacities. But now we worry about the delay, and we worry about the number of the out degree. Yeah, that's what we're worrying about. So, so now I'm going to present to you the different topologies, and this topology is the best topology because it achieves both achieve the trade-off of delay and out degree. But this topology is built upon these two topologies. So I'm going to discuss each individual topologies. Okay, so let's look at the balanced mesh topologies. Okay, so if you look at this topologies, so here's how the data dissemination work. And okay, so the source send out X1 over here, X2 over here, and this is basically just straight multicast. It's gonna go this node will stream X1 here, and this node will stream X1 here and X1 here. And so now these two branches right here, this branch have X1, this branch have X2, and so all this node does is going to stream X2 over, and this node, what this node does is stream X1 over. So now this node will receive complete data. So you can see that all the node here receive complete data. The problem is this node do not receive complete data. Okay, so now this node will stream the data from X2 up to this node. This node will stream the data from X2 up to this node. And you can show theoretically that every single node just subsequently just stream the data received from other branch to the node, the parent, the grandparent, the great-grandparents. You can actually do all of this. Okay?
How does each node go exactly?
So each node would have an ID. Each node would have an ID. And so, for example, this node would have its parents. This node would have its own parents. It have associated with an ID. So when we construct the graph, so suppose we have know everything about the graph. We know the topology. So for a moment, suppose every node know complete information, know the entire graph. Right? Now we solve that problem later. But okay, so this node would forward to here. And you can show that, in fact, this topology is optimal, equal 1. Yeah. Okay. So yeah. So if we can guarantee a certain delay, that's really tough. Really, really tough. So all we can guarantee that the delay is an order of log n, right? So you're right. It's tough. I try to work it out, and it turned out to be always humongous optimization problem. And worse yet, it's an integer optimization. So actually, but if you do it this method, well, you can guarantee that delay is on order of log n rather than n as a chain. Yeah, where b is the degree, the output, the degree of the node. So the delay n is the number of node, right?
N is all the degree, right?
No, b. B is the out degree. Okay. So in this case, b equal 2. N is number of node.
That means if you have a larger out degree.
Yes, right? Because it's the number of path, number of hop that it travel will decrease for the fixed number of n.
When you have a larger out, long
No, but the aggregate, each of these links right here will have many more coming into it. Each of link is slower, but the link, the receiving rate, will have many of these slow coming in. Slow rate link coming in. So it's the same. It will be the same. Okay? So we actually can show that this is equal 1. So that means it's optimal. You can't do better than that in terms of E. Right? It turned out that the only two nodes that is not sending at full capacity, this node and this node. And this node sending at the capacity of B minus 1 over B times C, its own capacity. This node also sending out at B minus 1 over B times C. So only these nodes are not sending at full capacity. But that is acceptable. It's still optimal because otherwise this node would send the data back to the source node. And the source node doesn't really need the data. Okay? So we can prove this. So here how it works. So you see it's the source sending out through here. And then it's going to connect through here. Yeah? So we can prove this quite easily. Yeah? So this topology is optimal. But there's big problem with this guy. Right? Big problem. Not many nodes, not any scenario you can form the exact equal number of nodes like this. Right? 3, 4. 3 you can, 4 you cannot. 5 you cannot, right? So it's very rare that you form this topology. So okay, it's drawback. The number of nodes has to be of this form. No good. The entire mass maybe need to review if a node go out, you have to recompute it somehow. That's bad. Not suitable for dynamic environment. Okay, so now let's look at the cascade balance mass. Suppose the number of nodes does not always equal, you can't always build a perfect mesh like this for a number of nodes. Well, whatever number of nodes that you have left, you're going to build another one exactly like this. And then whatever other one you have left, you're going to build another one. Okay, and then you're going to connect this guy with this guy. Now, notice that this guy and this guy before have extra bandwidth that I told you about. So now it's going to form the band. I'm going to send to a new root node. The same thing happened here. This guy and this guy have extra bandwidth. So now it form another tree. Okay, so now you can prove that this is also optimal. So now you can accommodate arbitrary number of nodes. But here's come the problem. There's always problem, right? Look at the delay. We can prove that the delay before was log n. Yeah, the delay in this case is actually log n square, on the order of log n square. Log n is good, but square, I don't know. It's still pretty much a lot of delay, right? So can we do better than that? Right? But so you see the algorithm, right? The fundamental thing here is that because this node and this node have extra bandwidth left that we have not been used, and that's why you can use here. But every other node has already been used up its own bandwidth. Yeah. So now drawback. Well, long delay, and also this type of topology is also messy when a node leaves. You have to review every single mesh. No good. Okay, now I'm going to introduce an unbalanced mesh, and this is what we implement because it's practical. Okay, the idea is to basically achieve incremental insertion and deletion of nodes. Is to you notice all the mesh that I cascade. I don't let it cascade for a long time. I let it cascade only for when the number of nodes reach a certain threshold, and then I destroy it and then reattach it to the big node in some smart way. Okay. And I show that it's still E still equal 1. Okay, so that's the idea. Okay, and in particular, if the number of nodes in the cascade mesh equal to b squared. Remember, b is a constant. So if b equal 2, b squared is 4. If b equal 3, b squared is 9. It's still a constant number of nodes. So it's scalable. Okay, so now I'm going to show you the algorithm for doing so. Okay. So here we have an unbalanced mesh. So here originally we start with the balanced mesh. Okay, now suppose a node coming in, node 15 coming in. So then it just join here as a new root node. Okay, just like the cascade balance mesh. Now another node coming in, node 16. So now it's forward all the data to node 16. Notice that so far, all the nodes, so far this is still equal 1. The only node that did not send anything is this node. But we know that there always will be one node that have extra bandwidth. Okay, so far it's still optimal. Okay, now the 17 node coming in, you have something like this. You send A here, send B here, and this node exchange. So this node have half the bandwidth, this node still have half the bandwidth. Okay, so far still optimal. Now the fourth node coming in, now fourth node is B equal 2 in this case, so the B squared equal 4. So here's the fourth node coming in, it's going to break the entire node and attach to this place. I'll show you. Let me go back here and I'll show you why it's possible to attach. Okay, first, you see this link right here? We're going to remove this link. Okay, let's remove that link. Remove that link and this link. So I just remove this link and that link. Okay, now I'm going to attach, and then I'm going to attach something like this. So this is a fourth node. I'm going to attach this guy to this guy to this. Okay, this guy to this guy. Well, I'm going to pre-attach like this. This guy through here, and this guy go through here. Okay. Similarly, you can do it for this guy also. Okay. Now, why does it work? Well, before you remove this link, right, from here, this link is responsible for sending the packet from this side to this guy. So now you have this guy take care of that. Okay. And this guy right here. Now the link here will take care by this guy. The link here will remove, will sending from here to here. It will take care by this guy, sending up. And similar here for this node, it's the same thing. Well, it turned out that b squared is the only possible number that you can attach to the b squared number of node here. Is the only possible number of nodes, smallest number of possible node that you can attach to the big mesh to maintain equal 1. We can prove that. So that's why we just move. And then if you have another node, say, suppose another node coming out, we can form another tree, go from here like this. And here, okay, and here. And then they keep going, and when it breaks, it can start attaching to this node and this node. So keep going up until you, at some point, you're going to fill up the entire level. Yeah. So this you can prove that the delay is actually only log of Bn. Okay, and you can also prove that any point in time, the number of nodes that are affected is only B squared plus 2B. The order B squared plus 2B, and that's it. So it's not dependent on n. So that's good. There's a constant. So we can prove this. Okay. So how about deletion? Well, deletion is easy. If a node come out, suppose node 4 come out, well, what you do is you replace the node here, go up, replacing it, and then rebuild this. You rebuild this mass. So then it's still B squared. Because you know the number of nodes here is only B squared most. Number of nodes. So that's how you achieve minimal perturbation. Yeah? So the drawback, node must have equal upload capacity, right? Well, I told you in the beginning that, well, it is that, sometimes actually we want upload capacity to be the same, just to be fair, right? But what if we don't? What if some node want to contribute more than others, contribute bandwidth more than other nodes? What should we do? Well, it turned out that we can prove some theorem about what if we cluster high capacity, medium capacity into some cluster, and within this cluster, we actually use our method, and look at the outer cluster, we also use the same method. Okay, so it's kind of have this embedded structure in it. And it turned out this is optimal in certain sense. So I don't have time to go through it, but it is also, so you can build up the kind of like wavelet, fractal. And because each of these nodes are optimal, you can prove in some sense the entire thing is optimal. In some sense. Not in the sense that an equal one. Okay? Yes. So here's the deletion of the node, right? Yeah. So this node is delete. I'll just move this node up, swap with this node, and then I rebuild this tree. This one? This one?
Let's say if the upper cluster is of high density, lower cluster is of lower density.
Yeah. So in this scenario, we assume all the nodes have the same capacity. Yeah. So if this have lower bandwidth, this is high bandwidth, you don't want to swap this up. You want to take some other node, swap over. Yeah, it's not that simple. It's not that simple. Yeah. Exactly. I show you algorithm to get rid of that. Yeah. That's one of the most concern, because when you claim peer-to-peer, you make sure that whatever information you store at this node better be not global information. Because yeah, exactly. Yeah. So the previous slide, I call it hierarchical mesh, but for the time, for short time, so I won't present the result on that. But here I just show some simulation result of 5,000 nodes. So you can, here I plot the efficiency, and here's the L degree. And here I show you the efficiency. We want 1 is the best, right? So here is an optimized. This is optimized topology, where you have the basic topology. But now what happened is, well, like Jin said, what if the node above have lower capacity than the node below? You want to swap it. So here is the topology. Here's the result that from the optimized topology, where I actually swap the node so that all the higher capacity node end up on top of the tree and low and end up at below. So this is the result. And this guy is not, the purple here is the result from unoptimized. So here I assume bandwidth is randomly distributed plus and minus 25%. Okay? So, and here's the multicast tree, obviously. Multicast tree, the vanilla multicast. Obviously, the throughput gonna reduce as a number of L degree increase, because you have more unused leaf node. Yeah? So here, the efficiency versus variation. So what if I just go ahead and vary the capacity of bandwidth, because in real life you can't predict. So go ahead and vary it and see how far is it off from the efficiency. So you can see even if you vary the capacity bandwidth by 25% up and down, 25%, the efficiency can be obtained at like 0.8. So you're up 20% off the optimal result. So here the failure evaluation, where we actually send full error correction code onto all these different branches, and we consider that if one failure allowed, then if we only allow one failure, then of course the number of node effect going to increase. But if we allow at least 2 failure, then of course the number of node effect going to decrease, right? Because this graph you can think of this is more FEC, less FEC, and less FEC. Yeah, that's basically. So you want to evaluate the resiliency of this. This is all simulation. I can just skip that. So now, so those are just simulations. MATLAB simulations and NS simulation. But we want to know what's a real thing look like. So we implement a experimental system. Now it's deployed over Planet Lab, and then we find out that for every node to keep track of information, that's a tough thing. Okay, so what we think that the better architecture would be a hybrid architecture where you have a supernode or supernodes, which handle all the connection management and all the information. But basically, it maintains the global picture of the entire network. Okay, so if you have video conference, 15 people, 20 people, no problem. If you have 100 nodes or 1,000 nodes, you might want to have more than one supernode. Okay, so supernode would be handle all the connection management and all the security. So we want to develop into a product, and that's why we take this approach that works, that actually robust. Okay, it may not be theoretical, interesting, but it will work, right? So our approach is a hybrid P2P framework. So we do all the management, we centralize it, but we have P2P data delivery, and this will give us performance, and we also handle security quite easily in terms of no authentications and all that kind of thing. Okay, and we also can upgrade all the software really easily because all the intelligent algorithm reside at the supernode. The regular node is very dumb. It's just act like a router. Okay, so we actually build different session managers into our system. So a supernode can hold multiple sessions. So you can have multiple video going on at the same time. You can do a lot. So we have architecture that do a lot of these things. Okay, so now just show some result of the real result on the Planet Lab. So this is a 15-node topology. So here's the average upspeed for 15-node topology, and we compare against vanilla multicast. So this is our approach. Of course, this is the branching factor or the out degree. Of course, our is perform much better. This is just the upload speed. So similar for download rate. Our also perform much better. Okay. Now here's for throughput evaluation. Again, here's the branching factor here. Okay, here's the time taken to transport a file. Okay, again, so vanilla multicast take a lot longer than our. So notice that the time, the throughput decrease as the branching factor increase from vanilla multicast because now all the leaf node is unused. Right, because the more leaf node, there are more leaf node. So that's why it's just increase. Okay, but our system stay constant because E always equal 1. Right? So here's the average join time for different nodes. So the average join and leave time, because you also calculate a different join time, leave time. When the node first coming in to a system, it has to contact the supernode, and the supernode allow it to join or not. So you have to calculate all the overhead of sending packet back and forth and calculate on average, how long does it take for a node to join a network. And so we plot the node number. And so the thing is, it looks jagged, but the thing you should get out of this graph is first the order of magnitude. So it takes less than 1 second. That's what you should get out. Okay, the second is you notice sometimes you have a dip and sometimes you have a peak. It's basically because depending on what position you're in. If you're at the position when the node got the entire mesh, got destroyed entirely, it's going to take longer time to rebuild. That's what you should take out of this picture. It looks messy, but it just shows you the order of magnitude and where the peak are. That means depends. So if you have the node that almost complete this tree right here, you have a new node come in and have to break, then that's where you have a lot of node you have to reconnect, b squared plus 2b. Okay, and the reason it takes this long because for every connection you have to authenticate that connection to make sure that the node is there. That's why it takes that long. Okay, so here's an interesting other. Oh yeah, so you can see it. This is packet loss rate versus bit rate. So we did this experiment. Here's a kilobyte. So you have to multiply this by 8. Okay, here's a packet loss rate. And here we put FEC, 30% FEC, here this line. This is a packet loss rate, recoverable, okay? And here's a without FEC. You can see that there's a trend. If you send higher and higher, you get more packet loss rate, okay? So at 170, so that corresponds to about 1.6 megabit per second. Yeah, so you can see that. Well, this is just this is the graph that shows the practicality of this. Yeah. Percent, yeah, that's percent. Yeah, from Planet Lab, that's percent. And this is average over all the nodes.
So you are thinking
UDP. Yes. It's, yeah. Send at whatever it receives, it will send at that. It send as fast as it can. It send as fast as it can, but because it's restricted by how fast it can receive. And that is restricted by the source. The source sending out at this rate. Yes, we have our system, we have all of that, but we just didn't, we don't show here. We sort of actually measure the bandwidth and swap node dynamically also. But that's not very researchy, so I didn't show that. At least in this talk, it's too long. But we are still working that result. We have that result, but it's not, my student and I don't think it's accurate. Planet Lab node is very, it's fluctuate, the bandwidth fluctuate all the time. So this graph right here is generated by Phil here. And he also noticed that sometimes, this is already average over many times, but sometimes, depending on the day of time, you know. So you see this peak right here, probably one bad node that caused everything. So it's not meaningful, but the idea is here you just see the gap. The idea is just show you the gap rather than a particular point. No, the entire. No, per link would be more efficient, but we use the entire. We just encode the entire source and just send it out. But per link would be more efficient because you would know exactly what link caused problem, and you would adaptively change it. Yeah.
So where you have a video conference where every node is a graph structure
yes.
for each node at the
Yeah, so it is true. So I just talked to Phil this morning. We have the theoretical result for that, but we haven't built it in. Yeah, we actually can do some smart reversing, reversing of the direction. So basically we keep the same structure of the graph. We don't change much, but we have algorithm to reverse the forwarding path to make every node receiving become a source node by slight change, and we can guarantee E is still optimal. I mean, E still go 1. Okay, but it's a current work. I have to work out some detail. Yeah. But another way, the easiest way to do this is like replace the source node with the, if you just swap it, that's the easiest way. If you just swap it, and then you're done.
You're assuming there's one
at one time. Then you just swap it, and then you just keep swapping the source node. You can do that easily. But the problem is that, well, you swap, that takes some time. Is there a smarter way? Right? So we thought about that. And actually we're planning to build a video conferencing system where whoever talk, you would have high resolution video, and other people who sit in background have low resolution video. And we should do time interleaving. So we can support a lot of DSL clients also. Right? Because this is built based on the upload, the bandwidth limitation is upload. Sorry?
What data size?
Data size, yeah, it's kind of large. So you can see some demo here. Actually, did he get it work?
No.
You don't want to go more than that. Yeah. So, then that's probably the reason why the fragmentation caused a lot of problems. The packet loss. That's why the loss rate a little bit high. I was thinking, why is it so high? But we can reduce that. But that's usually for audio you would send only like maybe says maybe 280 byte whatever, just a sample of 20 millisecond sample. Yeah. but this is just test. This is where we're supposed to do a demo, but this UDP port is not open here. Okay, so anyway, I have a lot of other things that I like to introduce. A lot of other research that I've been doing beside this. So this is kind of old work, like a year and a half ago. So I have sensor networks that I do energy efficient coding, routing coverage with Professor Bose. Also, I do some network coding right now. I have students that try to work on network coding. That would be, I would love to collaborate with Microsoft people on network coding, because, and also on the previous talk, because there are a lot of unsolved problems also. Then I also do mesh networks. I actually download the Microsoft mesh network and try out we build our novel application based on Microsoft mesh network. We're testing it out right now. And basically, I should do a theoretical work on quality of service for video transmission. And another interesting that our lab does is you do secure signal processing algorithms. So the idea is that, hey, you have an image, and I have an algorithm. Suppose you have a red eye in your image. I have an algorithm that removes red eyes, but you don't want me to see the image. How can I do it? The answer is surprisingly, yes, I can do it. You can send me something. I don't need to see your image. When I meant I don't see, I mean that you have the algorithms. But basically, you never send me the actual image, the bits of the image. You send me something else, but I'll be able to use my standard algorithm to remove the red eye. So basically, it's information hiding, but you still get the picture that you want. Okay? So we have a class of signal processing that you can do this securely. So, and that's it. So thanks for attending my talk. And if you have any question, I would love to collaborate with Microsoft, because I'm at OSU. I just joined OSU, and OSU is rather small. They're actually hiring a lot of faculty now. They try to drive OSU to the top 25. So I'm one of their first victims. Yeah. So they hire in CS. They hire 4 faculty last year. And in EE, we are still looking. I'm still looking for very good network researchers. I'm still looking. We haven't found it yet. We interviewed like 10 of them, but I guess we're picky. Yeah. So thanks again. So, do you have any questions?